move forward. So my first order of business is to introduce Steve. Steve is our Director of Environmental Services. He's been with us for about 24 years. Steve is a scientist. He has been very active in drinking water issues, drinking water quality issues here in California through a number of affiliations that he's worked through, specifically with the Association of California Water Agencies. But he is also very active nationally with the Water Research Foundation and the American Waterworks Association. So Steve's got a PowerPoint presentation. He's got about 20 slides. He should be able to get through that in about 20 or 30 minutes, depending on how quickly he moves. And then after that, I'll be back up again to introduce John and kick off the discussion. So Steve, if you would, please.
Can everybody hear me? Yes. Good. All right. Thank you for coming out. I know Monday night football, and you have all busy schedules, but we do think this is a very important topic for us. I'm glad you're here, and let's go ahead and get started. Just a little outline. We're going to talk about the characteristics of chromium, the regulatory process, the health effects. I'm always asked about health effects, the occurrence. Where does it occur in the valley? The way you remove it from drinking water, the treatment process, the costs, always an important thing, the next steps, what is the timeline for what will happen next, and then there's going to be a good discussion period. All right, chromium's been here long before we were here. The sediments in the California area happen to have a very common rock that contains naturally occurring chromium. The California state rock is serpentine, and it has elevated levels of chromium. And in fact, those rocks and other ultramafic rocks that like it occur at the margins of faults. And we have a major fault system going through this valley. So as you get close to the margin of that fault, you're going to find those types of rocks that have a little bit more chromium in it. And we're talking about parts per million levels in the soil. And then that dissolves into the water in the parts per billion range. And I'm going to talk a little bit more about what that means. Chromic oxide is the 9th most abundant compound in the Earth's crust. It occurs both as chromium-3 and chromium-6. The only difference is a few extra electrons. So you're missing 3 electrons and becomes chromium-6. And it converts from one form to the other depending on the environment that it's in. Chromium-6 is more soluble. It dissolves easier. So in water, you're usually going to find it as chromium-6. In rocks, you're usually going to find it as chromium-3. But again, depending on what environment, it'll convert from one to the other. We find it naturally here, and there are other sources. In other areas, there are industrial sources where there's been pollution incidents. They're pretty isolated, but there are those that occur in the state, but that's not the case here in the Coachella Valley. Total chromium in water is equal to the chromium-3 plus the chromium-6. Chromium-3 is essential. We need it in our diet. We use it to do multiple metabolic functions, including the production of insulin, which we need to regulate our blood sugar. It's in our food, it's in our supplements. The daily recommended dose is between 50 and 200 micrograms per day. Okay, a microgram, when it's dissolved in 1 liter of water, a little over a quart, is equal to 1 part per billion. 1 part per billion is about 1 drop in 10,000 gallons of water, a small swimming pool. So it's a very small amount, and the body does need that chromium-3. Chromium-6 is, because it's missing those 3 electrons, it's a little less stable. So it's more reactive. It's easily converted to other things, and it's more reactive with cells. And that's one of the things that we're worried about, and some of the scientists are worried about. It is easily and rapidly reduced to chromium-3. And One way to do that is put it in a reducing environment. Low pH, your stomach is designed to reduce chromium-6 to chromium-3. It happens rapidly, within seconds. Vitamin C, another excellent reducer. Infant formula has to have vitamin C in it. Vitamin C is a great reducer, reduces any chromium-6 to chromium-3 within seconds. Organic matter is another. It doesn't have to be a low pH environment, but if there's food present, you're going to have those type of compounds that will reduce chromium-6 to chromium-3. Once in the body, they've done studies, plants and animals, when it's inside the plant and animal, it won't, once it's converted to chromium-6, to chromium-3, it won't convert back to chromium-6. So that's important in how they evaluate this compound. So when the regulators, there's folks that spend their lives developing regulations. So we have thousands of contaminants, chemicals, and elements. So they're going through that list and trying to determine which ones might be a concern to regulate. And there's a list there of some naturally occurring compounds, radon, vanadium, strontium, and all those occur in groundwater. Again, very low levels. So they're going through that list and trying to identify which ones might be a concern and need to be tested. And usually when they do their risk assessment, they look for human data, but often they'll use the animal data. And so they expose the animals to high doses and they see if there's an adverse response. And if there is, then they want to see, okay, is that something that occurs in water? If it doesn't occur in water, there would be no need to regulate it. So if it does have an adverse effect, it occurs in water, then the process continues, and you have to see, can you measure it? Can you measure it at these low levels, and can you do it practically? That's important. The next thing, can you remove it? Can you install a treatment process to feasibly remove it from the water? And then, of course, they get to the cost. Is it economically feasible? Do the benefits justify the cost to regulate that compound? And then it starts all over, and new data comes up, and then they may need to look at that same constituent again if there's new data that changes their evaluation. So where are we on the chromium? Total chromium has been regulated since 1977. The federal standard is 100 parts per billion. The state standard is 50 parts per billion. In 1999, we had a rodent study that presented an issue. Is chromium a concern when it's ingested for carcinogen, for causing cancer? We then had a blockbuster movie, Aaron Brockovich, so a lot of interest was in this compound. Our lawmakers in California adopted a law that requires the scientists to develop a drinking water standard for chromium-6 by 2004. Problem was they didn't have the science to do that. So they embarked on a rodent study, a large rodent study, and in 2008 that rodent study was completed, and that provided the information they needed to calculate the risk. 2009 it was draft the public health goal. That's the level at which there's no risk. It's a calculated level based on animal studies usually. And so at that level, it doesn't mean what's safe and what's dangerous. It's the level at which there's no risk. Now, typically in life, we don't do things with no risk, but we try to manage our risk. So that's part of that regulatory process. You have this goal where there's no risk. By the way, it's 0.02 parts per billion. That's 20 parts per trillion. You can't measure it that low, but it's a goal. That's the no risk level. So now the challenge is, where do you set the level that you can feasibly do it economically, technically, as close to that goal as possible? That's where we are. Then they got sued. The state was sued by the National Resource Defense Council and the Environmental Working Group because they hadn't set that standard yet. So they were sued. So they came out with their draft chromium-6 limit here in August. And that's where we are. We're in a 45-day public comment period for this draft rule. And the draft number is 10 parts per billion that you'll hear a lot about. So where does it occur in California? Chromium occurs throughout the state above levels of 1 part per billion. That's the detection level. But only about 60% of the sources have been tested. It's not regulated, so there's no requirement to test it now. But there was back in 2001, they wanted to get some information. So there was some testing done back then. And that's what most of this data is based on. We know that chromium-6 accounts for almost all of the total chromium in water. That's important because we've been testing for total chromium since the 70s. There's a lot of data on total chromium for a lot of wells. So it works as a good replacement. If you don't have chromium-6 data, you can look at the total chromium and see if you might have a problem with this rule. The state estimates about 311 sources have chromium-6 in the state above that 10 part per billion level. 67 would be above the 20. So the red, here we are in the Coachella Valley. Each dot is overlapped, so there's a lot of wells under those dots, but that's where our concentrations are. So looking at the valley here, I'm going to point out a few things important. This is up by the windmills. This is where we have been replenishing Colorado River water for about 40 years. This is the Salton Sea. This is Coachella and Indio, which we do not serve water to. That's why it's grayed out. The rest is all the well data that we have, including the Desert Water Agency's wells. The dark blue color is essentially no detectable chromium. The darker blue it is, the lower the level it is. So we have basically no chromium up here. And as you move down close to this fault, these red lines are the fault system. And you see the higher levels. And I've talked to the folks in Indio and Coachella, and most of their wells, not all, but most of them are over the 10. This transition area right here between green and yellow is that 10 part per billion range. So anything yellow and brown is all over that level. Interesting here. This is where we have started a recharge program of Colorado River water. It went full scale in 2009. It's just east of La Quinta. And that well there was about 15 part per billion about 5 years ago. And now it's almost non-detect. So we're seeing here the dilution from Colorado River water. Colorado River water has no chromium-6. So this whole area is the 40 years of Colorado River water that we've been importing and replenishing the groundwater basin. So we're seeing very low levels. Desert Water Agency has no wells over the 10. And that's a result of the benefits. The closer you are to that replenishment area, the lower the chromium-6 levels are. So about half of the water that we have 100 wells that provide water to the service areas. About half of those wells would be over this proposed level of 10 parts per billion. And our highest levels are about 21 parts per billion. So about half are over 10, half are below. All right, health effects. The state regulators and the state assessors, they're the experts on health effects. This is coming from their document, their public health goal report. They know that there have been poison cases. If you consume large amounts of chromium-3 or chromium-6, you start vomiting, and those are health effects. So they know that there are non-carcinogenic health effects at very high doses. But what's been studied the most is chromium-6 for the inhalation issue. For many years, since the mid-50s, it's been known that when you inhale chromium-6, it's a problem. Because we don't reduce chromium-6 to chromium-3 in our lungs. And our tissues they're very good at exchanging oxygen with blood. But they're also good at exchanging chromium dust in the chromium-6 form with the bloodstream. So they know lots of data on that. You work in a chromium ore facility, a chrome plating facility, painting facilities. There's lots of occupational exposure studies, hundreds of studies. You get cancer if you ingest that too much. Lung cancer, oral cavity is where the tongues turn yellow, just this high doses of chromium in the dust. So that's what we know the most about. What they don't know a lot about is ingesting chromium-6. There's been some studies, inconclusive. There was a Chinese study where they were drinking yellow water, and the author said there was no effect, and then some other folks re-looked at it and thought that there might be an effect, but not a lot of strong data, and certainly not strong enough to calculate that risk level, that public health goal. So they based it on the rodent study, and that data showed clear evidence, and we're going to look at that data, that it's a carcinogen. At these high levels, it's a carcinogen. So from that, they determined it's a possible human carcinogen. While they couldn't use human studies to calculate that level, they did use a national toxicology program rodent data. That was the one that was done in 2008. Meanwhile, EPA is evaluating not only that study, but also more recent study that's out. Several studies. And so they're looking at that data. We're expecting them to finish their risk assessment later this year, maybe next year. Right now, they're still looking at the most recent data. Okay. So this is the actual data from the rodent study that was used to calculate that no-risk level, 20 parts per trillion. So they gave rodents no chromium, 50 rodents in the test subject, and they look at the cancer, the tumors formed, benign and malignant tumors. The lowest dose they gave them was 5,000 parts per billion. So our drinking water standard is 50 parts per billion for total chromium. So they started 100 times higher than our drinking water standard at 5,000. This is actual potassium dichromate that was given to the rodents. This is the dose that they would have drank their whole lives. They would consume this from birth to death, and that would be the lowest dose. 10,000, 30,000, and 90,000 parts per billion. So looking at the data, the 5,000, no statistically significant difference from the control. 10,000, no difference. But here at 30,000 and 90,000, these yellow cells showed there was a statistical significant effect as a result of consuming these levels, 30,000 and 90,000 parts per billion of chromium for their whole lives. So that was clear evidence that it was a carcinogen when ingested, and that's the data that is being used to justify the standard that's been proposed. Well, the Chinese village, back in 1987, their levels was about 2,000 ppb. So it was yellow, just a little lighter than this. But yeah, you won't find anything. We have a current drinking water standard in California 50, and in the country it's 100 parts per billion. You won't find any water over that. It's already being regulated, so the chromium-6 could not be above 100 parts per billion, or it wouldn't meet current drinking water standards. So yeah, you won't find anything like that in tap water. No.
That color is totally attributed to the chromium?
Yeah, chromium is Greek chromo, which is color. Chromium likes to react with a lot of different compounds and form all different colors, like green and yellow. And it depends on what compounds it binds to in what color it's going to be. So yeah, chromium was an interesting early contaminant that a lot of scientists were very interested in because of its different colors that it does with different reactions. This was a 2-year study. 2 years is about how long these rodents live. It's a very standard length of study. And if you look at the survivorship, no difference in survivorship. About half of them died here, and about half of them died here. There was no statistically difference in survivorship. The same number of rodents lived through the study, no matter they were here or here. But they did have tumors on them. And in the mice, it occurred in the small intestine. So you got the stomach, The stomach's not made to absorb. It's made to secrete. It's actually made to not absorb because of its environment. Then it goes into the small intestine. That's the very next thing. That's where you're absorbing the nutrients that you digested in your stomach. So, small intestine. Not in the stomach, not anywhere else, but they got it in the small intestine. And this new data EPA is looking at evaluates this. How did these rodents get the tumor? It's called the mode of action. So that's what this new data, and there's some very good scientists that believe that there was a threshold. And when you overwhelmed the rodent's ability to convert chromium-6 to chromium-3 with these high concentrations, chromium-6 passed through the stomach and into the small intestine where the absorption was taking place. And it killed cells. The cells then have to be replaced. When you replace cells exponentially, you're increasing the chances of a mutation. And the mutation then forms cancer. That's what one group of scientists, very well respected, believe. And then there's other groups of scientists say, well, maybe that's one mode of action, but maybe there's another. We have to be safe. We have to be precautionary. So, that's the two sides of that issue. And you hope you're trying to balance. The lawmakers have told the scientists, adopt a chromium-6 standard. That's your job. The lawmakers have told them to do that. We're the only state, by the way, that's going through this process. So, what they want to do with these studies is have all the factors the same except for that dose. So they want to make sure the control animals and the others get the right nutrients, the normal food intake. They even measure the water intake, and that's why they didn't go higher, because when the water intake dropped, then their weights dropped. So they had to, in fact, with this study, they actually tested the rats at 180,000 parts per billion. And they actually had data for that, but they couldn't use that data for the male mice because they lost weight so much that they weren't drinking the water. So they had to throw out that data. Okay. All right, the treatment. So Glendale, lots of work on how you figure out how to remove chromium-6. That's all happened in the last 12 years. They identified 3 technologies there. And that was because they had some industrial pollution. These are very industrial sites to remove chromium-6 not because of naturally occurring, but because there were industrial contamination. And not just chromium, they had other things in the water too. They pilot tested these two type of treatment processes, and they developed some cost models. How much does it cost to remove chromium-6 from water? So that's some good data. We happen to have our own data. We were the first in the country to install treatment plants that remove both naturally occurring arsenic and naturally occurring chromium. About 12 years ago, when they lowered the arsenic rule, we also knew we had chromium naturally occurring in the area of the East Valley, where we have naturally occurring arsenic, kind of by the Salton Sea, Mecca, Thermal, Oasis area. And so when we were doing our testing, we also wanted to test to see if we could remove chromium. And we did find a process, same one that the Glendale is using, an ion exchange process. And this is what a treatment plant looks like. It's about $6 million facility. And you can see it's a very large facility. And we're going to take a look. We have 3 facilities in total. And about $20 million we've spent so far to comply with that arsenic rule, and we're going to look at some data too. Okay, so inside the treatment plant, these are the vessels that do all the filtering, and it's an ion exchange process, kind of similar to a water softener. Instead of removing calcium, which makes the water hard, it's removing sulfate and a little bit of chromium and arsenic. Little beads, little tiny beads are in there with lots of surface area. And that's where the chromium and the sulfate and the arsenic attach to the bead. And they trade those chloride is let go and it accepts sulfate. So it's an exchange process. So that's why they call that an exchange. And here's some actual data. This is the influent level of chromium coming in. You can see here's that magic 10 level. And sometimes it's below and sometimes it's above. This is variability, natural variability that you see. The analysis itself, it's part per billion level. You get natural analytical variability that's several parts per billion. So this is important. It'll come up later. And then this is the water coming out of the plant, which is down close to zero. Not quite at zero, but pretty close. So it's doing a good job of removing. This is what the arsenic and chromium looks like when we combine it with iron. Kind of looks like rust. It's like 99.9% iron. And we press it, and that's where the arsenic and chromium ends up, and that's how we have to dispose of it. And it's quite a process to get it to that point, and it's not cheap. Well, that is hazardous waste, because it's over 5 parts per million of arsenic or chromium. So it goes in a barrel. It goes to Beatty, Nevada, a Class 1 hazardous waste facility. And it's actually not the most expensive part of the disposal process, because we have to use salt brine to get it to this point. And it's that salt brine that we have to dispose of that's really expensive. And that we drive up to Los Angeles, and it ultimately ends up in the Pacific Ocean. It's the clean salt after we've removed all this. So there's actually 2 waste streams that are generated. Yes, but remember, this plant was constructed to treat for arsenic, because arsenic, we used to have a standard of 50. And in 2001, they lowered it down to 10. And down in the Mecca and out there by the Salton Sea, we had levels as high as 25. It met the 50, but when they lowered it down to 10, we had to install treatment. So this was designed to treat for arsenic, which it does a good job, but also it removes the chromium. We happen to have chromium also present.
So like a byproduct, you're telling me, you didn't design it to be.
Well, we did, because we knew this was 2001. Aaron Brockovich was 2000. So we looked in the future.
You didn't build this because of the movie.
No. We had to build a facility to remove arsenic. Now, we wanted to make sure we didn't pick a treatment process that only removed arsenic but didn't remove chromium, because we would be sitting here today, and if they lowered the standard to 10, we'd say, man, we got to go out and put another treatment plant. And where are we going to put this treatment plant? We don't have space. So we wanted to make sure we reasonably forecasting what we expect we might have to regulate for. Chromium was on our radar at that time. So we wanted to...
One well or 2 wells? How many are funneled through this treatment?
Two wells go through this facility. It's 4,000 gallons per minute, which is a large facility. At the time, it was the largest. I think it still is. All right, let's move on. Research. So we're not just satisfied with that. We're also doing some nationally supported research. We're looking at 2 other treatment technologies at a well here in Palm Desert and one in the Desert Hot Springs, or close to Desert Hot Springs. And it's looking at, these are the columns. We're testing different beads like that. And they work. They also remove chromium-6. Looks like they're about the same cost, maybe a little bit more expensive for this one, but maybe easier to operate. And that could be important. So it may be more expensive to install, but easier to operate, which could help with the reliability, which is important. You got to factor that in. Yes?
Federal government support this?
No, we're getting Water Research Foundation matching funds. So half of your money and half of the Water Research Foundation. So it's about a $500,000. There's actually 2 research projects going on at the same time. So we lobbied for that, and it really helps out to have the additional funds. And the whole country is looking at this data. Down the road, there may be other states that may have to meet the standard. Yeah. Okay, so costs. Let's move to costs now. How did the state develop their costs? They used that data from 2001, 2002, mostly, so it's old data. And based on that data, they believe we have 27 wells that would be impacted at this 10 part per billion. Our data shows we have 57. So their cost estimate's missing a lot of data. We drill new wells all the time. We replace wells all the time. So when you go back 12 years, you're going to miss a lot of data. So that's a big issue with the cost estimate the states used. Water supply conditions. They used formulas and calculations based on population to try to predict what our well sizes are. They think our wells are about 325 gallons per minute. Our wells are actually average 1,900 gallons per minute. The size of the well means how big of a plant you got to build. It's a lot more expensive. That's a big cost issue. They had that data in their regional offices, but that would have taken a lot of extra time, so they used a formula calculation to try to predict what the size of our wells are. Same thing for the amount of water we use. You saw that industrial-looking facility with all the tanks that was out in the open. Well, we couldn't put that next to someone's home. Palm Desert wouldn't approve something like that. We'd have to have a building architecturally compatible. They did not include land and buildings in their cost estimate, and that makes a big thing. You put a building around these facilities and the land. You need land to put the facilities on. Most of our well sites are too small. So those are some of the issues with the way the cost did their estimate. And this is kind of the summary. So statewide, can you see okay? Everybody see okay? The estimate the state has for the large public water system category, that's what we have, a large public water system, is $64 per year. That's using those assumptions that they use to kind of predict the cost. If you use those same assumptions, but then you plug in this is statewide. Now this is using the same state method, their same data that the state used, but applying it to our system. Because remember, this is an average of the whole state. So looking at our system using their data, it's about $130 per person per year, per customer. So per home, per business, per year. Now, using the same cost formulas that the state used, but plugging in the actual well data, the size of our wells, the number of wells we'd have to treat, you get up to just over about $550 per customer per year. So that's the kind of the comparison of using their numbers to the real data. Okay, what's it all about? So this is the benefit. Estimated theoretical annual cancer cases avoided. So at that 10 ppb level, the states estimate 12 avoided cancer cases. Statewide, if all those sources were brought down to meet the 10 part per billion. So that is the benefit, 12 statewide avoided cancer cases. So you use the same, all the states estimating process and apply it just for the systems we provide, and it's 0.52 cancer cases per year avoided. But remember, they left off a bunch of wells of ours. So you add those wells in, and it goes up to about 1 cancer case per year because we have more wells that would be need treated, so that's more benefit. So about 1 cancer case per year for our water systems. So now they look at also how much does it cost to avoid that cancer case. That's a good way to look at how we use monies to protect public health. Statewide, they estimated $13 million per avoided cancer case. That's, they've done estimates of the value of statistical lives, and it ranges from maybe $8 to $9 million. So, it's within range, $13 million. Then you apply that same state method to the water systems we provide, and that would equate to $22 million per avoided cancer case. But again, that's using their assumptions. Then you plug in actual well data for our water, the size of our wells, how many wells, and it goes up to $57 million per avoided cancer case. So that kind of shows you how important getting the right costs when you're doing your cost-benefit assessment is. So we want the state to use the right cost numbers. We don't know what level they're going to come out with. They're going to look at the costs and weigh it with the benefits. If the state thinks that $57 million to avoid a cancer case is a justified cost, then let's make sure they're using the right numbers. That's what we're asking them to do. So we're going to do some compliance testing, finish our treatment research. We're going to look at, our well sites. This is a little well building, too small for putting a treatment plant on. So this is Desert Willow. We have 3 wells in this area, all too small to put treatment plants on. So in this way of consolidating, we would take water lines through the streets to combine these flows to this vacant land where we could build a treatment plant. That would be one approach. Another approach would be to condemn the home next to the well and put the site so we don't have to build all these water lines. So those are all approaches that we'll have to look at. There's going to be we're going to have to look at funding approaches, reach out to the public, and eventually develop an implementation plan, but we don't know until they set the standard. So we are going to be submitting our technical comments by this Friday. That's the deadline. We're going to be testifying in LA. We tried to get a hearing out here, but they wouldn't. So we're going to go to LA and testify. The public should, view their website. We have some comment letters there you can look at. If this is important to you, submit comments. This is your window to provide feedback to the state on what you think. We should all be asking for an accurate cost-benefit assessment. I mean, that's fair. It should be protective and it should be affordable. Local governments, we've been meeting with the local governments. They've said their legislators are going to submit letters. The state's going to look at all the comments. They're going to prepare a revised limit if it's warranted, or they'll stay with the limit that they've done. Now, this is a little interesting twist. Because they were sued, they're going to have to respond back to the court with their responses to comment, and the court could set a deadline. Usually it takes about a year between a draft rule and a final rule, but the court could limit them to a certain number of months to come out with the final rule. And eventually it will be effective, whatever they end up with. So, discussion period. I probably went a little long. Let's let...